So I'm going to do a quick overview of my Christmas tree project. This is a really simple little ornamental Christmas tree. It really was not designed to be budget friendly or immediately marketable in any way. It was kind of one of those things that just hacked and threw together with parts I either had sitting around or that were cheap enough that I didn't really care if I bought them for this project. So I got here on my Windows computer a quick overview of the layout of the part. It was built on a two-layer OSH Park run. It's about 3.5 by 4.25 inches. It ended up being about 70 bucks for 3 boards, which really isn't all that cheap. I probably could get them a lot cheaper somewhere else, like JLC or something like that, but for the timing that I needed them, price was right. Um, so generally, there are 47 bidirectional LEDs on this board. Each one of these LEDs can be whatever I decide to put in there, but realistically, I designed it for a 1206 size LED. The ones I used are available in green and yellow, red and green, red and blue, so I can get any variation here. So I could make them all red and blues if I so desired, but I ended up just mixing it up and putting in one every three. So this was red, blue, red, green, green, yellow, so on and so forth, and just placed mostly randomly around the board. It's designed to be either an ornament or a standalone board ornament. So there's a little mounting hole up top. You can put a thread through it or something like that. It does not require a plug-in. One could easily put it on a 3-volt battery of some kind, say like a AA battery pack or something like that. Tried to keep it pretty simple. It kind of stands up on its own here with the power jack, but really not. The way we set it up in the window, I just leave it in the window. Um, so there's an EJ5. It's designed for an EJ508A power jack that I use commonly in a lot of my projects. This is a standard 5.5 by 2.5 millimeter power jack, center positive. You can find them anywhere. This power switch, and then the major component of logic is an AT SAM E51. This is a way overkill processor for what it is, but I had the schematic symbols, I had the parts. They're only $4, and when I was looking at a board cost of 20 something odd dollars plus $10 in LEDs, $4 for the controller didn't really seem too bad, especially given the fact that I already had code, support base, knowledge, and experience with that particular part that I could just code it up real quick and be done with it. There's also a partless contact for programming using a JTAG tag connect, but I used the 6-pin version, not the 10-pin version, so I have my own adapter cable for something like this. If I had to do this differently, I would probably optimize on cost more, probably focus on the PCB manufacturing, get that as cheap as possible. I might use different LEDs, maybe something like a WS2812, which are the RGB addressable ones in a serial path. Then I could probably use a much cheaper processor as well, like say a SAMD21, which those can be had for $1 a pop. I'd also use resistor arrays. I just would have had to buy resistor arrays. I have resistor arrays in 330 ohms, but I ended up using 10 kilo ohm resistors for each LED because I don't want to overtax the current capabilities of the processor. At 3 volts and 10 kilo ohms, you're looking at maybe a milliamp or two. Whereas if I use 330 or 1K resistors, I might be going anywhere from from 10 to 30 milliamps or something like that. There's a reset switch here as well that I can probably get rid of as well. I probably could have gotten a few extra lines out of it if I'd have, reused the SWDIO and the twin wire interface for that's used for programming. The let's see, whoops, I don't have the top layer turned on. It makes it kind of hard to see, but the top layer is actually what is a common bus across all the LEDs. You'll see that all the LEDs are hooked up to this power plane, which is actually controlled by a pair of MOSFETs here. So to explain that more, I want to go with the schematic. In the schematic, I tried to keep as simple as I possibly could. SAM-D50 or SAM-E51, programming header, a couple of bypass popcorn, a reset resistor. Probably could have left this switch out simply because the reset is pulled over to the ICSP connector. And then each LED goes to a resistor, which then goes to one of the pins. The rail, as I have called it, is just a power inverter. And I put in a power PMOS and a power NMOS transistors in here that are 20 volt and 5 amp rated in a SOT23 package. I'm switching this at about 10 kilohertz, so I don't have to worry about any fancy switching speeds. Just as a quick note, because I'll cover it in the source code, LED 48 is the pin. I probably could have called it something else, but I was just lazy. That's PB03 on here, which you'll see in the code. Let's see. It could be done probably a little bit better, possibly, to use maybe 5 volts. One could easily use, say, a WS2812 with a 5 volt processor and then just use a USB connector and not have to worry about a regulator. This is all 3.3 volts, and I had a trio of 3.3 volt not regulators, 3.3 volt wall warts, so they output 3.3 volts for exactly what I needed. So I just used those. There's a billion and one options. Those I looked at on DigiKey for those particular power adapters, and they're about $8 or $9 a pop. So I would not normally buy those. I would try and get like a cheap USB 5 volt power supply since it's so ubiquitous. Let's see what else. Yeah, mostly it was just all simple. You can see my schematic symbol here is one from a different project for where I was doing some audio DSP stuff, where I have an I2S interface and stuff, and I specifically designed the symbol for that project. I wasn't going to go about and just redo a symbol just for this. So the code is extremely simple. I'm just going to open in WordPad. I do this on my Linux computer normally. It's based off of an Atmel start setup. So in the Atmel start, it's really simple. It's only got the timer set up in the code base. In my final release files, the Atmel start and the AT start and AT zip files are included. But there's really not a whole lot to this code base. There's a timer with some volatile integers, just to run that, a timer, a callback function, some variables that actually store the states of all the LEDs. So these are 32-bit integers. So there's 32 bits and 32 bits, which is the entirety of the entire port registers. So the SAM-E series has they have 3 port registers, but only 2 of them are used for the one that I've got. So if we go back to the schematic here real quick, you're going to have PA00 through PA31 and PB0 through PB31. That's 64 bits total. Some of the Atmel SAM parts or microchip AT SAM parts do have a PC register, but this one does not. So I didn't end up using it. And I'll explain why I'm doing it this way. I wanted to keep it really simple. So I've got what I call the status registers for, if I had all 64 IOs, I could theoretically control them with this if they were all on the same 32-bit register ports. So by default, side 1 starts off and side 2 starts on. These are bidirectional. So what we do is that every 100 microseconds, I toggle back and forth between that power inverter here. So this toggles every 100 microseconds, bringing the far side of the LED either high or low, and then we match the port registers to either the inverse of what we want. If we want it to be on, we invert it, and if we don't want it to be on, we don't invert it. This will make sense here, I promise. So the interval here, so the internally on the microcontroller, the timer is set to a 10 microsecond tick, or the internal interval of the timer is 10 microseconds, and then we set the counter on the timer to 10, which gives us one tick of 100 microseconds. My labels are kind of screwy here because I was just coding things directly. But one of the things I did is instead of telling Atmel start that everything was an I/O pin, because you can go through and laboriously call each pin LED1, LED2, so on and so forth. I just went bare metal to an extent with this. I start it with the Atmel init and I use some of their stuff for the timer, but then I just go straight here and I say everything's an output. I don't care. Everything is an output. Now there's only 40 or 51 IOs if you include the twin wire interface and the reset pin or a few other little weird things like that. So theoretically, I'm setting bits that don't exist here, but I think that's actually a little bit of a randomized benefit, and I'll explain why in a second. But here I'm setting all of them to outputs. And here I've actually, it's setting the output of port PB03 to logic level high. That means that when this is high, the rail is low. So any of the IOs that are high will light the LEDs on that on the side one, or whatever you call it. There's just an infinite loop here, wherein there's a timer. It says if this timer, which it's incremented in the callback function, if it's no longer equal, hey, we have an event. Otherwise, just sit here and do nothing. Reset the timer so we don't do it again until the next timer interval resets. If we get 100 counts, that's 10 milliseconds. So this is where I screwed up in my comments. I'm too lazy to fix it. And we reset all the timers back to 0 so we don't get any overflows, because really we don't care what time it is. We don't care how long this program's been running. And then if the milliseconds, now remember this is not 1 milliseconds, this should be 10 milliseconds. So if millis is 10 or tens of milliseconds is greater than 10, that's 100 milliseconds. We basically reset the timer, wait for the next 100 milliseconds, but in the meantime generate a random number between 0 and 64. And then if the number is greater than 31, we use the B registers. If it's less than 31, we use the A registers. So up here, there's 64 bits, and we can control either one. And all we're doing is shifting the value of the register over to the right and extracting its 1 bit, and then saying shift that bit back, but toggle it. So all it's doing is saying if random pulls up bit 3, it's saying get bit 3, flip it, and put it back, so that we turn if it was off, it turns on. If it was on, it turns off. We do this again for the second sides. Every 100 milliseconds, we're doing both A and B sides. That's all there is to it. So every 100 milliseconds, it's taking 2 bits and flipping them, and it's random. It says, okay, well, I'm going to flip bit 3 and I'm going to flip bit 27. Doesn't really matter. And it just goes on and on. Now this, can't collapse this in this WordPad editor, but if I'm just going to delete that just to make this a little more readable. So we don't care about any of this. So this executes, make it real simple here. This is going to execute every 100 microseconds. We start out at state equals true or state equals false, and we set all the outputs, out 0 and out 1. So this is the lower 32 bits. So this will be port A 0 through 31 and port B 0 through 31. And we use side 1A on and 1B on. So if any of these bits are on, the output of the inverter is going to be low, so those bits will be high or whatever we want them to be. Then we flip the state, and then 100 microseconds later, we'll do the exact opposite thing. where we give the bitwise inversion of our values. So if we want side 2A bit 1 on, it'll actually set it to 0. It clears that bit that's going to the inverter, which means the rail is high. And so if side 2A on bit 0 is equal to 1, it gets written to 0 as port PB00, and the rail will be 1. So as a result, that LED will be on. And that's really all there is to it. And it just generates a kind of a cool little twinkling effect. I kind of tweaked with the numbers a little bit until I liked what it looked like. And that's really all there is to the code. So let's go take a quick look at it.
The Christmas tree isn't very visible during the day, but if we turn the lights out, it's much better with the lights off. A little twinkly. You can see it goes from different colors, or multiple different colors, and some of the LEDs, it can't really be seen in the video very well, but sometimes their multiples are on. So right now this one here that's more purple is both red and blue at the same time, whereas this one right here is blue, and so it's just changed, and now that one's back to red. So all of these LEDs are multicolor, so eventually they'll randomly turn on and off. Green, red. This one here is probably a... Oh, that one's actually got green on right now as well. And so they're all bicolor LEDs. Alright, all shenanigans aside, this is the actual PCB for the final product. So there's a power switch here. Turn it on. Lights up. As you can see, when it starts up, the first initial line of code, if you go back and rewatch portions of the video, is that we turn all of one side on and all of the other side off, which makes it handy for debugging initially when testing out the PCB. So what I was doing a lot of time was turning it off, turning it back on, and just looking to say, is everything turned on? Because all LEDs on one side should be turned on, no bidirectional or anything like that. Initially, I did have a few problems because I had like a short wire or a resistor that didn't get completely soldered, so it made it reasonably easy to debug. One thing you'll notice, if I reset, turn it off, and turn it back on again, the pattern is always the same. I can even hit the reset button. There's a reset button here on the back side. It's harder to see here, but you'll note, like, say this yellow LED here always turns on a few seconds after I reset it. So the pattern is always the same. But after 10 hours of running this, you won't know what the pattern was, and you won't know any difference. So I really was not worried about it being true random or anything like that. It's just a pseudo-random number. It's probably based off the serial number of the device or something like that as the random seed, because I found that this tree did not do the same random pattern that the other trees did that I built. So overall, though, really nothing too hard to solder here. I used solder paste and hot air and a pair of tweezers. And I just went around the whole outside of the board. Let's see, this was I think this one's red-green, yellow-green, blue-red. No, this is blue-red. This is blue-green, or red-green, yellow-green. And then I just repeated the pattern as I went around. So because it's 48 LEDs or 47 LEDs, but they're bidirectional, realistically there's about equivalent of 96 LEDs or whatever, or 94. The processor was not too difficult to solder either. A couple of solder bridges when I did that, but standard JTAG tag connect. So when I program it, I can just, if I can see it here, program it in, program it, be done with it. I'm using a 6-pin tag connect. I believe I mentioned that. And I've got my own little adapter board here that I use so I can use either the 10-pin versions or 6-pin versions. And this is a fake knockoff, but it works, programs. So Other than that, I could easily put the battery pack on the back side here. You could leave the power switch off or use something with an integrated power switch. Doesn't really matter. But yeah, I'm really pleased with how it turned out for the time frame that I built this in. The biggest, longest wait was getting it back from OSH Park. And even then, given that I'm in Oregon and OSH Park is up in Portland, it's not that long of a trip. And amazingly, it came here fast, even with all the Postal Service delays. Yeah, that's about it. Oh, the PMOS. So this is the PMOS FET right here, the little SOT 23. I had some obsolete parts from ST Micro, I think. So there's a PMOS in here, and then there's an IRMLL 6244 or something like that. They're both like 6.5 amp MOSFETs. Way overkill for what it is, but it works. So, anyway, Merry Christmas, Happy New Year, and thanks for watching.